This tutorial will be covering when the ideal gas law breaks down and basically defining or distinguishing what a real gas is and what an ideal gas is. So, as the title implies, real gases are when the kinetic molecular theory breaks down. And so, as a background, you should have watched our kinetic molecular theory tutorial and the five postulates of the kinetic molecular theory. So, if so, recalling the kinetic molecular theory, the assumptions for it to be ideal are the molecules do not attract or repel, the collisions are perfectly elastic, and gas molecules themselves have no volume. So, there are cases when those start failing. So when does that start happening? It's when the gas molecules start exhibiting intermolecular attractive forces. That's like the main time that a ideal gas stops behaving according to the gas laws as we know them, Boyle's law, Avogadro's law, and Charles' law. So on this slide, I'll be covering several different gases and analyzing their intermolecular attractions, and then we'll put them on a PV graph, and then see how they behave when they're under high pressure. Okay, so so we'll say O2 for instance. It's we'll make like a little chart here, London dispersion forces, and the type of polarity that the gas may have. So first of all, when we analyze London dispersion forces, we're looking at number of electrons, total electrons, not just valence. So total electrons, oxygen has 16, and that would imply weak London dispersion forces. And the polarity is that it's nonpolar, so it's just O2. Okay, and there's no dipole arrow to draw there. Okay, so it's nonpolar. We'll be looking at CO2. So a quick analysis of this shows there's 22 electrons, and this is also categorized as weak London dispersion forces, and it's nonpolar as well. Okay, however, keep this in mind that it has six more electrons than oxygen. Also, what helps the London dispersion forces for CO2 is it has a linear shape. Okay, and it's composed of three atoms, while O2, so this is three atoms, while O2 is just two atoms long. Okay, so this has a little bit more surface area for those London dispersion forces to work to do what they do, to cause their induced dipoles. So this has more surface area for those to occur. So it's going to be a little bit better because it has more electrons and it's got three atoms long, so it's a longer shaped molecule. So another molecule we'll be looking at on our PV graph is neon. So this has 10 electrons and it's monatomic, so this is weak. And another thing we could write here about it is it's monatomic. So it's a gas molecule made of just one atom, and it's obviously nonpolar. This is kind of not really appropriate to even say it's nonpolar because it's not bonded to anything, so obviously it can't be polar. NH3 is uh, is 10 electrons, so its LDFs are also weak. If we draw the structure here for NH3, okay, this is ammonia, and we see that it's got dipoles here, and not only that, but it's got a special dipole where it's N to H, so that the difference in En there is this is like a 3.0, this is a 2.1, so it's zero point 0.9, which is relatively high for En, and as we know, the N to H bond it can do hydrogen bonding. So what we're gonna see here is these different gases. If you put them under high pressure, you're gonna see that. And let's recap the main postulates. So in our previous tutorial, I listed five textbook postulates of the kinetic molecular theory. So just to recap those here, like the main important ones. So the assumptions for an ideal gas the assumptions are that there's no attractive or repulsive forces between, I'll write BTW for between the molecules. Secondly, the collisions are perfectly elastic. So after they hit each other and the sides of the container, the gas molecules continue to show the overall same kinetic energy. That's kind of like the more technical way to say that. Okay, so they don't lose any kinetic energy after they collide. So the gas molecules uh, themselves have no volume, okay, relative to their container. So molecules, and just atoms and molecules are so tiny that compared to like a can that they might be in, the actual molecule itself is insignificant. However, we'll see that under certain conditions, you can get these to start happening. And once you start getting those to start happening, then this breaks down, and this breaks down. And it's mainly because of intermolecular forces start happening under two conditions. So IMFs, I'll write it up here. So IMFs, so keep this in mind as I go over the graph on the next slide. So IMFs start happening primarily two times: when there's high pressure or a low volume. Okay, the other time that IMFs start happening is when it moves slower. And how do you get them to move slower? Is you reduce the temperature. So when you lower the temperature, okay, then the molecules will start going so slow that they start exhibiting London dispersion forces. Okay, and once they start doing that, they become inhibited from making collisions. Okay, and the collisions are no longer perfectly elastic. They do start showing attractive forces, and under high pressure, you can only squish a molecule as far as you can't like squish a molecule to obliteration. So you'll get to a point where under really small volumes, that the molecule of the gas actually does play a role in the amount of pressure that is observed. Okay, so let's go ahead and look at this on a graphical representation. So if you had uh, so I'm gonna show um, graphs of the different gases. So I had four gases. Okay, and I'll show ideal behavior is that if you multiply P and V, so this is Boyle's law. If I multiply P times V, I should get some constant. Okay, I'll just call it A, some constant. So when this goes up, this should go down to compensate, and then you end up getting the same number. And conversely, if this goes up, then this should go down, so you again obtain the same number. It equals a constant. This same number happens to be 22.4, the molar volume. So if I make a line right here, okay, if I multiply P and V, okay, I should get this same number here, okay, 22.4. However, there's gases that deviate, and these are when they become real gases, okay, and no longer they behaving ideally. So you'll get one that shows deviation right here. Okay, so I'm gonna write question mark. Okay, and then your guys' task is to go back to the last slide, analyze their LDFs and their polarity, and match each gas with the correct graph. So the gases I listed on the previous slide were CO2, um, Ne, and this is in no particular order, O2, and NH3. Okay, and I'm going to draw four lines here, and you have to match the correct gas with the correct line. Okay, so our next line here, and I'll give you some hints and pointers, things to think about. Okay, so this one I'll write another question mark, and our third gas deviates from ideal behavior. Okay, but not as much as the blue one and the orange one. Okay, and then we have another gas that actually positively deviates from the ideal gas law or from the expected value. So right question mark here. Okay, that line didn't stay for me. Okay. So what we're looking at here is this gas right here. So I'll give you some pointers here. Okay, this gas right here is actually has the most negative deviation from ideal behavior. This line right here represents ideal behavior, meaning it follows the gas laws, Boyle's law. Okay, so what about this gas causes it to exhibit under very high pressure? So this is under so these gases when you start getting around this range right here, you're under very high pressure. Okay, so very high pressure results in when you multiply these two numbers, it results in a lower than expected answer when you multiply P times V. So that means under high pressure, the volume ends up being much lower than expected. Okay, and that occurs for the green one and the blue one, but this one's the most. Okay, so see if you can match the correct line here. And the other hint, of course, is to review the previous slide that you guys have. Okay, so that's the end of our tutorial, and we'll see what you come up with there.